Okay, class, today is a big day. Le Chatelier's principle and rice tables are on the agenda. By the end, we'll be able to explain how the relative equilibrium quantities of reactants and products are shifted by changes in temperature, pressure, or concentration. We're also going to explain how the change in equilibrium constant with change in temperature is related to the enthalpy change of the reaction. So some of this is review. Especially some of the Le Chatelier's principle stuff, but that does not hurt to jog our memory for it. And then rice tables. You may or may have not had experience with rice tables before. They're fairly straightforward, and there's some tricks that will make it fairly easy for us. I highly suggest watching this and continuing to watch this if you're about to do the lab, because the lab does have some rice tables we'll have to do. So I want to make sure you are prepared for that, okay? Le Chatelier's principle. If a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of that disturbance. Okay, that is a mouthful. Essentially, all that means is that if we put something into our system, we want to relieve that stress, right? So a couple of the key things you'll typically see: pressure, an increase in pressure. Pressure increase typically causes us to shift to the side with fewest moles. All right. We just spent a lot of time with kinetics and catalysts. I've got good news for you. Catalysts do not affect Le Chatelier's principle. It does not affect K. It does not make K larger or smaller. Catalysts have no effect. And you may think that's strange, but if you think about it, all a catalyst does is speed up the reaction. It does not change the reactants and products. So it just helps us reach equilibrium faster. So there's no effect on K. And the other thing we'll see a lot is that temperature. So temp, and we like to treat temp as a reactant or product. And we most often want to think of this in terms of delta H. So think endo, exo. If delta H is positive, we know it's endo, and it's going to be considered a reactant. If it's negative, it is exothermic, meaning heat is being given off, and this is our product. Okay, so when we come to our balanced equation, we're going to make sure we rewrite it with our delta H, our heat, as a reactant or product, and then we'll be able to see more clearly how temperature affects it. All right. So we have some practice here. Predict the shift in equilibrium position that will occur in each of the following processes when the volume is reduced. Interesting. Well, we just spent time talking about temperature, pressure, and catalyst, but we didn't talk about volume at all. So think for a minute. If volume is going down, what does that do to the other variables in our system? If you're thinking about gas laws, a decrease in volume means an increase in pressure. So really this is saying that our pressure is going to increase. Now this is very important for paying attention to states of matter, because that only affects our gases, okay? So the first one, if we look, the preparation of liquid phosphorus trichloride by the reaction P4, which is a solid, 6 chlorine gas, and we end up with 4 PCl3, phosphorus trichloride, which is a liquid. Okay, so if we are trying to think about how this will affect the shift, what happens to my reaction when I increase pressure? I shift to the side of fewest moles. Well, if we look at the total moles, I've got 7 total moles on this side and 4 total moles on this side. So there's going to be a shift. This is going to shift to the right with a decrease in pressure. Now you have to just remind yourself that solids and liquids aren't in the equilibrium expression, so while we'll see a shift to the right, we'll be able to notice the gas disappearing, but we may not be able to tell that the liquid is going up in concentration just because the concentration is already very large. Okay. Preparation of gaseous phosphorus pentachloride according to the equation below. This one's tricky because we have all gases. So if we decrease the volume, remember that a decrease in volume results in an increase in pressure. Which way is this one going to shift? This one also shifts to the right. We've got 2 total moles on the reactant side, and we got 1 mole on the product side. They're all gases. This is going to be a shift to the right. I want to relieve that stress. There's too many gases. We gotta shift to the right to alleviate that. If you think about it too, if we're increasing the pressure and we have more reactants, those reactants are twice as likely to collide with each other and make PCl5. So it makes sense that we would shift to the right anyway, because collision theory says that we would now have potentially more interactions due to the increase in pressure. All right, the reaction of phosphorus trichloride with ammonia. What will happen in this scenario if we decrease the volume? This one's tricky. You gotta look at the total moles. We got 4 total moles on this side, 4 total moles on this side. We're equal. So if we decrease the volume and increase the pressure, there is no shift here because there is no side of fewer moles. It's going to stay just like that. The overall pressure is probably going to increase, but we're not going to cause any reactions to happen. It will stay at equilibrium. Okay? So here's one of the ones where we're specifically looking at temperature. So we want to predict how the value of K changes as the temperature is increased. Okay? So we'll do the first one together. Like I said, we're going to take our delta H value and make it part of our equation. So here I see that as a positive value. Is that endothermic or exothermic? Endothermic. Good. So with endothermic, we have 181 kilojoules plus N2 plus O2, and we get 2 NO. All right, so if we increase the temperature, this is going to cause us to have a shift to the right, right? If we have heat as our reactant, increasing our temperature means we're increasing the amount of heat available as a reactant. We're going to shift to the right, okay, to make more products. So if we think about that, be careful. This says predict how the value of K changes. Well, if I'm shifting to the right, is K going to increase or decrease? K is going to increase. If I'm shifting to the right, products go up, reactants go down, and if I look at that, I know that K is equal to products over reactants. Mathematically, this makes sense. A smaller denominator means a larger K. So K increases in this scenario. Okay. So let's go ahead and rewrite the second one together, and then I'll let you take your best guess. All right. Where does heat go on this side of the equation? Well, it's negative, so it is exothermic. So we've got Negative 198 becomes a positive 198 on the product side, okay? If I'm increasing temperature and heat are on the product side, which way is this going to shift? It's going to shift to the left. I want to relieve all that extra heat. I'm going to shift left. What does that mean for my reactants? Reactants go up. Products go down. And if I think about that, that means I have a larger denominator. K is going to decrease. So you can reason both qualitatively and quantitatively with this. If we wanted to plug numbers in, we could do this with our Q quotient, or we could just kind of reason if we know these couple of ideas here. All right, the big one, here it comes. And hopefully it all comes back to you. The rice table. Other places may refer to it as an ice table. I like rice because it includes the balanced equation, which we sometimes forget to do. The rice table, writing a balanced equation is our first step. Then we fill in our initial concentrations, that's I. So I is initial concentration. C is determining the change that takes place in terms of X. Something I want to point out here is that it's proportional to the balanced equation. So X is always proportional to that balanced equation. We need to make sure that we account for that coefficient there. And then E, express the equilibrium concentrations in terms of X. So when we're solving these types of problems, we want to set up our rice table. At the same time, we also want to set up the equilibrium expression and set it equal to its K value if it's given. That will save us a lot of trouble. If we're already given equilibrium concentrations, we can skip down to the E line and just fill them in. But sometimes they may give you equilibrium concentrations and you'll have to work backward to determine the change, or the X. It's very popular for them to give you an equilibrium concentration for only one of your reactants or products, and you have all your initial concentrations, and then you'll have to determine the equilibrium concentrations for the other 2 or 3 reactants. If you're given a K value, then use it to solve for X, and then you can also use X to calculate equilibrium concentrations. There's a typo there, I'm sorry. There should be an M in there. Man, okay. Some hints. These will make a little more sense as we encounter these scenarios. If K is very small, that means the reactants are largely favored. That means that the equilibrium concentrations aren't going to be very different from the initial concentrations, but they are going to change a little bit. So X may be negligible and therefore ignored when we are doing our calculations. This is the small k approximation. The way I can liken it to is like an estimation of sorts. If we had 1,000,000 cookies and someone ate one of those cookies, and you were to estimate how many cookies you still have, well, we know for exact we have 999,999, but we would still estimate that as about 1,000,000. Right? Our concentration is changing to such a small degree that we can ignore that X because K is very small. Barely any product is being made in that scenario. We also have situations where sometimes the initial concentrations are not going to be 0. So you might need to find Q first in order to determine which direction it shifts. And for some of the really tricky ones, I'm sad to say the quadratic formula is going to become your friend. Let's take a moment, take a deep sigh. I know. We'll make it through it, I promise. You'll see the quadratic formula a lot more, especially when we get to the acid-base equilibrium for weak acids. Those are going to be real fun. I don't know, I find it satisfying to solve those problems. It's a lot of work, but the math people will really enjoy those. So let's do 1 or 2 or 5 million. We're going to do rice tables pretty much from now until the AP exam. They will be your best friend. I would practice equilibrium problems, as often as you can, because It's one of the key components, and we will honestly, almost with 100% certainty, have an equilibrium problem on the exam. So here's one. It says a closed system initially containing 1.000 times 10 to the negative third molar hydrogen and 2.000 times 10 to the negative third molar iodine gas at 448 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration is 1.87 times 10 to the negative third molar for HI, which is our product. And they want us to calculate Kc. All right, well, the nice thing is they already gave me my balance reaction, so there's my R. I'm going to set up the rest of my table here. So I've got my I. I'm going to just kind of split it up this way. And I've got my C, and I've got my E. Now you don't have to make an actual table if you don't want to. If you want to leave the lines out and just have nice rows and columns, that's fine. But we want to put in our initial concentrations. So we've got 1.0, 1.00 times 10 to the negative third. 10 to the negative third, and then we've got 2.000 times 10 to the negative third. And it's really important that we remember to keep our things in scientific notation. Don't ignore the scientific notation, it's important. And then, this is interesting, they don't actually tell you your initial concentration of HI, they tell you the equilibrium concentration. So that actually goes down here in the E box. Oops, I'm sorry, gotta make sure I get the right number. 1.87 times 10 to the negative third molar. Okay. If they don't give you an initial concentration, we can assume that it is 0. So we don't have any HI to start, but we're making a bunch of HI as we go. I'm going to actually make this a little bit neater, so I apologize. 1.000 times 10 to the negative third. All right, that's a little bit more legible. All right, for C, we need to figure out our change in concentration. Our change in concentration is proportional to our balance equation. If we look at the moles, we know we're going to use some amount of H2. We're going to call that X. We know that's going to be proportional to the same amount of I2 that we use because it's a 1-to-1 ratio. So we can also say some amount X minus X. We're saying minus X because we know the equilibrium is shifting this way in this scenario. If the equilibrium was shifting the opposite way, then it would be a plus X. But we're not gonna confuse ourselves yet. We're just gonna make sure we can get down our regular rice table. All right, and then now on the product side. Now we lost 2 X's. We've got to get them back somewhere. Here we're going to make 2 times X. 2X is our change. And that matches up with our balance equation here because we get 2 moles of HI. Now the equilibrium concentrations of our reactants, we don't know them, but we can use our I and our C and combine them to make a nice equilibrium expression. So 2.000 times 10 to the negative third minus X is equal to my equilibrium. 1.000 times 10 to the negative third minus X. All right, so if we set up our equilibrium expression, we know that K is equal to HI squared. And those actually are concentrations, I'm sorry. Concentration of HI squared over the concentration of H2 and the concentration of I2. Okay? Now, they didn't tell us what K is, that's what we have to calculate. But we can plug in what's in the equilibrium section here. Now we know our equilibrium concentration for the top, 1.87 times 10 to the negative third molar, and that is what we are going to square. So So this squared. Now the tricky part is figuring out what to do with these x's that we have for our reactant equilibrium concentrations. Well, the nice thing is that we know that at equilibrium, since we had no initial amount of product, 1.87 times 10 to the negative third molar is equal to my change, right? 2x plus 0, because we combine those, right? Just like we did with our reactant side. So if we combine those, we really have 1.87 times 10 to the negative third is equal to 2x. Well, the nice thing is we can solve for x here. So divide both sides by 2, solve for x, and we get that x equals, I got to do the math, so let me pull up the calculator. 1.87 times 10 to the negative third divided by 2, we get 9.35 times 10 to the negative fourth. So 9.35 times 10 to the negative fourth, and that is my change. So that's my change in x. So what I can do is I can now plug this back in. I'm going to use a different color. I'm going to take this number and plug it back in here, and plug it back in here, and I can say 1.0 times 10 to the negative third minus 9.35 times 10 to the negative fourth. All right. So 1e negative 3 minus my answer, 9.35 times 10 to the negative fourth. And I get an equilibrium concentration. I'm going to erase this. I get a new equilibrium concentration for my H2. And that equilibrium concentration is 6.5 times 10 to the negative fifth. 6.5, I'm going to write just e negative 5. All right, and I can do the same thing for the other side for I2. 2e to the negative third minus 9.35 e to the negative fourth. Ooh, make sure I got my negative in there. All right, and I get 1.065 e to the negative 3. We can leave it just like that though, 0.001065. All right. Now I have my equilibrium concentrations and I can plug them back in here. So I've got 6.5 e to the negative fifth, all right, or e negative 5 in your calculator, and I've got 0.001065. All right. Now you can go ahead and solve. So we go ahead and solve. We've got 1.87 e to the negative third, and we're going to square that. And then we want to divide by 6.5 e negative 5 times 0.001065, and we get 50.51. This had 4 sig figs, so we'll stick with 4 sig figs. We get K is equal to 50.51. All right. So pretty easy to figure out your equilibrium constant. We just have to remember a couple of different steps. And once you have your equilibrium, once you have your X, your change in X, you can figure out your equilibrium concentrations fairly easy. All right, let's do one more. The decomposition of PCl5 occurs via this reaction. It's placed in a reaction vessel held at 250 and has an initial pressure of 1.10 atmosphere. And then when equilibrium is attained, the pressure is 0.33 atm. And they want us to calculate our Kp. All right, so let's do our table. PCl5, and we got PCl3 and Cl2. So the nice thing is you can still do this with pressures. So we've got our initial 1.10 atm, and we're assuming we had no initial amount there. And we know we're going to lose some amount x, and it's going to be proportional to the balance equation, so minus x, and you get plus x, and then plus x, because we gain 1 mole of each, okay? And then my equilibrium. So the nice thing here is they actually gave me my equilibrium concentration, all right, for PCl5. And then I know for now what I can plug in is plus x and plus x. All right, I'm actually going to cut back on some of the space. Well, the easy thing to do is set this equal to my equilibrium concentration. So I know 1.10 atmosphere minus x is equal to 0.33 atmospheres. Okay, well, you can solve for x. Go ahead and solve for x. All right, x is equal to 0.77 atmospheres. Good. Well, we know that our change is equal to 0.77 atmospheres, and we can plug that back into our equilibrium spot here. Okay, so we know that the equilibrium concentrations for PCl3 and Cl2 are equal to each other, and they are both 0.77 atmospheres. So if I want to go to calculate my Kp, you know that Kp is going to be equal to my products, PCl3 times Cl2 over PCl5, okay? So I can plug that in. I've got 0.77 atmospheres. So we can plug in 0.77 atmospheres. You could just condense it and say 0.77 squared, but I'm going to show both parts just so we can see the work. One for each. 0.33 atmospheres is my equilibrium concentration on the bottom. We plug in and solve Kp. What is Kp going to be equal to? 0.77 squared. Oop. 0.77 squared, there you go, divided by 0.33. And I'm going to round that. I get a Kp of 1.80. All right, so 1.80 is my Kp value. Okay, that is all for this play posit. The next one, we're going to handle a lot more of the examples from the NAMESY packet. So we're going to go over quite a few of those because the equilibrium concentrations and the rice tables will get a little bit more challenging. All right, have a great day.